and welcome. So we have been discussing the explicit upwind method. Just do a recap on what we did last. And we want to discretize, that is our aim, the linear advection equation. That was our equation, that is the time derivative of some advective quantity u plus c, which is the advection velocity, times the x derivative of this advective quantity. With the temperature, concentration, whatever. And we have been focusing on the case where the advection velocity is positive. And you did in the exercise 6 the case when the advection velocity is negative. And when it is positive, then we have the stencil. We write that in this form, where we have j, how to see from the j, and there is j minus 1, this one, and then we have here n, and here we have n plus 1. So from the known values at time level n, at j, and j, just the other way around, let's see, no, this is j and this is j minus 1, this way. J and j minus 1, we compute the value at the new time level, and we do that with then taking an upwind difference on that, from where the wind is blowing. And we argued then that we can get the formula, that is formula 18 that we used, then that we get the value at the new time level from the value at the old time level at grid point xj minus c times the value at the old time level minus its upwind neighbor, that is the left neighbor in that case. And c is the current number. So this, the capital C is the advection velocity times time step divided by delta x. So that's the ratio that our advective quantity u travels in the time delta t. That is c delta t. The ratio to the grid spacing is the current number. And then we did a von Neumann stability analysis on this, and we found that the amplification factor is the following. So that was the von Neumann stability analysis, and that was 27 that we derived last time. That this is, and we write it as beta, function of beta, which is k delta x. It is 1 minus the current number times 1 minus the cosine of beta, which is, you could imagine as the non-dimensional wave number. And we have here then something more, namely I sine of beta. So that means we have a real part and we have an imaginary part. And the beta, I just said it, that is k delta x. And now we were on the way to analyze this more. And we argued that this is a complex number, and like any complex number, we can represent this in the complex plane. So if we have the real part here, and we have the imaginary part here, then we can imagine that if this is then our g, our amplification factor, then we can represent it as a vector. But we can also imagine that it has a length, which is the absolute value, and then that it has a real part, which is then here the real part of g, and this is then the imaginary part of g. And they determine then the angle that we have here. If we take this, we have a tangent of the imaginary and the real part, we have an angle here, phi. So then we can represent this complex number by its absolute value and the angle. And that was the thing that we were doing last time and that we want to continue now. So that was the argument that, like any complex number, you can represent then the amplification factor g of beta as the absolute value. So that is then just this, the number, the length, times e to the I phi. And phi is then this angle. This is clear because this is the cosine phi plus I sine phi. So, and then we argued that the phi can then be obtained in our case, and that was 33. The angle for our amplification factor, which is called the phase angle, is then the arctangent, because the tangent is then the imaginary part to the real part. This to this is the tangent. And if we want to have the angle, then it is the arctangent of the imaginary part of g of beta divided by the real part of g of beta. So that is what we call the phase angle. And that is of our amplification factor of the numerical method. So what we are discussing is the explicit Upwind method. So that is the phase angle of our method. So of, say, it would be then of 18 of our method. Now we want to analyze this a little bit. And first thing is we want to see what is the absolute value. So the absolute value, and we can get that from here. So from the representation of the amplification factor, that is 27 that we have here, then we get that is then 34. So I think here we start now essentially with a new part, that the modulus of the amplification factor is equal to. Now, we have already, I think, done a little bit work on that last time. Let's see. Yes, we have already computed the modulus squared. So we just used that. That was when we derived the stability condition. We have already done that. So we simply take that, what we did during the derivation, we computed the modulus squared. We take simply the square root of what we got from there. And what we got for the modulus squared, taking the real part squared plus the imaginary part squared, was the following. 1 minus, now I write this here as 2 times, so that is what I think we also used it. This is 2 times the sine squared of beta half. So that is another way of writing 1 minus cosine. So then we get 1 minus c, and then we get this sine squared of beta half. So that was the modulus squared, and now we take the square root of that. So then we have the modulus. So what can we see here? We argued from the stability condition, c should be between 0 and 1. So this c should be between 0 and 1. So then this is between 0 and 1, and this is then also. And this is positive or 0, so we have here something that is positive, or in the best case it is 0. So, but anyway, this will get negative. We get a negative number here, subtracting from 1. So we get here something that will be lower than 1, when beta is larger than 0. That is the distance, the wave numbers that are interesting, from 0 to pi for beta. So that means we have here something that is damping. Each time step, the solution for this wave with the wave number k will be multiplied by this factor. So that means the wave will be damped. We shall compare that with the exact wave number. We shall find out that that is not damped. There is no damping, and it should not be, because as we saw, we are solving the linear advection equation. It's simply advected. Some profile is advected. It is not changed. So no Fourier mode has to be damped. But this method damps. And we shall see how that is done in a minute. But before that, we also want to see what is the phase angle. So here we have the modulus of the method, but we also want to see what is the phase angle. So we have to compute them this year. And we find out the following. It's for the phase angle. So it is the modulus, and here we have done the phase angle. Simply have to take what is over there, that is then the phi, is then the arc tangent of. Now we have to see what is our imaginary part of g. Here we see it is minus c times the sine of beta. That is the imaginary part. So that will come in the numerator, minus c times sine of beta. And what is the real part? That is here, 1 minus c times 1 minus cosine beta, or we could also write it in this form. And then it will be 1 minus 2c sine squared of beta half. So then we have used this trigonometric formula to replace the 1 minus cosine by this. So then we have to compute this expression here to get the phase angle. And we shall compare this to the exact values. And the exact values that we have already worked on last time. So the exact modulus, take that first, modulus of E of beta, that is then what I think we have not yet done that, but the G exact. And that is what we derived last time. That was actually e to the minus I c beta. That is something that we derived last time. So that is when we plug in a Fourier mode, which is continuous in time, u hat of t, e to the I k x, into the PDE, into the linear advection equation. We found out that we get this. So that means the exact modulus of this is then, we have something like that. This is cosine the argument plus minus I sine the argument. If you take that, the modulus of that, that is 1. So we have simply that this is simply 1. So and that is, we have no change in the amplitude. And that is what we just said before. If you doubt that, just use Euler's formula. Cosine of the argument minus I sine of the argument. Take the absolute value, then you get cosine of sine beta c beta plus squared plus sine c beta squared. Cosine squared plus sine squared is 1. So then we can see that we definitely do an error here, as already mentioned, when we use the explicit upwind method, because there we do not get 1, except for beta equal to 0. And this will be 0, and then we get 1. Now, what about the phase angle is clear, that we see very quickly. The phase angle here, that is then minus C beta, that we had already last time. That is the exact phase angle. Yes, we have already discussed that. So that is then just to have that clear. The exact phase angle is then the 31 that we had last time. We call it phi e for exact. That is minus, we write it with the beta, we write it in this way. So and now the comparison is done of the phase that we get from the numerical method, that is 35, with respect to this. So that means when you look in the book, you will see that G of beta modulus of the amplification factor and the ratio of the phase angle from the numerical method, in our case for the explicit upwind method, is related to the exact phase angle. They are shown in so-called polar plots. We'll see that in a minute in the textbook. That is Fletcher, Tannehill Anderson, current edition of 2013. That is the one that is referenced, but you can also use the older edition. They did not change much in that. So let us look at that now. What are these polar plots? What is meant by that? So let's see. So I've prepared something here. If we start with the traditional plots, then it would be something like that. So these are not polar plots. These are the classical plots where we plot the non-dimensional wave number beta on the x-axis, and we plot the modulus of the amplification factor on the y-axis. So here we see the results for 4 current numbers, because this is clearly dependent on the current number. We see that here, which is this coming in here, and which is then plotted as a function of beta. So if we start by 0.25, we have that here. As we increase, we get here, and then the 0.75 goes back on the same location as 0.25. That is when you plug in here 0.25, you get the 0.27 here, and the other way you get here the 0.75, and here you get the 0.25. So therefore it's the same. And the 1 is exact. For current number 1, the method is exact. So that is the classical plot. That is not the polar plot. If we look at the polar plot, it looks like this. So polar plot means that we plot now everything with respect to the angle phi, and the angle phi is now starting from here, from 0, and is moving like that. So for example here at phi half, we have these values that are given then by the distance from the origin, and we see that we get damping for 0.25. Let's see, that was 0.5, that is 0.25 and 0.75, and that we get 1, which means no damping, for the current number 1. So that is how we have to interpret that. We take an angle, go round, and then the distance from the origin tells us what is the size of the modulus, G of beta. That is how we shall interpret that. And when we are here looking at this and we look at the current number 0.5, we see that we get 0. So that is then a case which is does mean that we have full damping. And that is for beta equal to let's see. That is beta equal to pi. That is the largest weight number, non-dimensional weight number that we can represent. So then this will be 1. This will be 0.5. This will be 0.5. So we will get 1 over 4. With this 4 we get 1. So we get 1 minus 1 is 0. So in that case we get complete damping of the waves with the weight number k beta equal to pi. That is what is then meant by this. So that is then completely different for the exact solution. There we have no damping at all. So that is the way how this is represented as a polar plot regarding the modulus. Now we want also to look at the phase error. And the phase at first, the traditional representation, where we have again the non-dimensional weight number k delta x here on the abscissor. The ordinate, we have now the phase angle, phi of beta, divided by the exact phase angle, what we call phi e. So we are looking now at this ratio here. And then we see for the current number 1, we have 1. So then the numerical phase angle and the exact phase angle are equal. So then we are exact. If we have, let's see, I don't see my 0.5 at the moment.
I think it's on the red line.
That's a good point. Yes, thank you. Good. So that means this is exact then. So for this current number it happens to be exact. So that's a good thing. It can happen. Sometimes we have surprises. And so that means for that current number, the phase error, that we don't have any phase error. It's perfect. For 0.25, then we have the lower values, and actually we go here to 0. That corresponds that the wave is not moved at all. It should be moved. Any wave should be moved with the same advection velocity, but this one, if we get a 0 there for the phase, it means it is not moved at all. It is just stationary. So the wave numbers corresponding to the highest wave number that we can represent are simply stationary, which is not good. If we look at the situation for 0.75, we have the opposite. Here, the propagation is too low, so we are propagating the wave numbers in this region here too slowly. So when they have a wave propagating, the numerical wave will arrive later. It is too slow. It is a lagging phase error. For 0.75, it's the opposite. It's going too fast, so it's not good either. So anyway, we have done some errors, and what we saw, I showed you some example last time in the numerical simulation. The phase error did not show up in the examples that we studied. What we saw definitely was the dissipation error. The amplitude of the sine wave got damped very much with this method. And the phase error is there, but it is not showing up that much as with other methods. We'll see examples of phase error today. So that is the way how you can interpret then the modulus of the amplification factor and how you can interpret the phase angle and relate that to the exact phase angle. That tells us whether amplitudes are damped, the modulus of G, and whether the propagation velocity is too slowly. We have lagging phase error, or too fast, we have leading phase error. So then we have then done the analysis, and so that is then the result, and you will find the polar plots. I think we need that also. That should show you that also. That was the number 2. So that looks like this. So that is now the polar plot of the same thing that we saw before. Again, the interpretation is we look from the origin what is happening. For the phase angle phi equal to 0, the values are all 1. That means the phase angle is exact, is equal to the exact phase angle, because we are plotting this ratio here. If we go along with phi, for example, if we take here pi half again, we see that we get errors here. We get an error for the 0.25, and again we see here the one for 1 and the one for 0.5, they are exact. So 1 is the correct value. The one above, that is the leading phase error for for the current number 0.75. So that is traveling too fast. And then as we go here, we see here that for 0.75 it's getting more faster and faster, so almost 20% more than it should be, while for square number 1 and 0.5 we are exact, and again we see here no, the phase angle is 0, no movement at all for the waves with the wave number pi. And you see these kinds of plots in the book. They have almost for any of the schemes, any of the scheme they have done these plots. For the modulus, telling us about the damping, the dissipation error, and about the phase angle, telling us about the dispersion error. And so that is the way you can then interpret these results. Okay, so that should be enough for the moment. So then we have done now a quite careful analysis of the explicit upwind method. So now we want to see for alternatives other methods and see also their performance. We have now been looking at the explicit upwind method. Now we want to look at the implicit upwind method and see how that works. So let's see. We got the explicit upwind method by taking an upwind difference on the spatial discretization. We shall also do that here. But instead of using the explicit Euler method in time, we shall use the implicit Euler method. So that is the only difference. Use the implicit Euler method. And the same as we did for the explicit upwind difference. In space. And then we'll have a standstill. We start with that again. Let's see that here. We start here with the values at a grid point j, xj, and the time level n. We want to determine the solution at the new time level. And instead of using now the neighbor, here we have j minus 1, and here we have n plus 1, the time level n plus 1. And instead of using now the value here, we use now the value up here. So we have this stencil here. That is the difference. So we use now the difference, we take the difference not at the old time level, as we did here, with the explicit upwind method, but we take it at the new time level. And then we get the following scheme, which is then the implicit upwind method. We have a similar time discretization as ujn plus 1 minus ujn divided by delta t. That is the discretization of du dt. Now we take c. Now we take the difference, again upwind, but at the new time level. So that is the difference. So taking it at the new time level. uj minus 1 at the new time level, divided by delta x. So that is all. And in our notation, using the nj, the number of grid points, starting from 0 to nj, we can use this method from grid point for j1 nj. If we would do that with the j max, then this would be number 2, and this would be j max. So that means we can use it at the right boundary, because it needs only, like the upwind, explicit upwind method, only values to the left. That is as physics tells us. It should be like that, because the characteristics go from the left to the right. So, and we can then also write this scheme in the form where we write everything unknown on the left-hand side and everything known on the right-hand side. And that is then the following form. So let us see, what do we get on the left-hand side? If we multiply by delta t, we will get delta tc divided by delta x. It will be the current number. And here we'll have the ujn plus 1. And here we will have also, we'll get a current number also with that. So we'll get 1 plus the current number, ujn plus 1. So then we have taken this and this into account. Now we have to take this into account, and that will get a minus. So we get a minus the current number, ujn plus 1. And now we bring this on the right hand side, then we get the ujn. So that is another way of writing the algorithm. That would be, say, the way that we use then for the discretization, as we shall see. And sorry?
J minus 1?
Yes, thank you. You're right, thank you. Good point that we need. So and this is valid for j again from 1 to nj. For j equal to 0, we use the boundary condition. We don't need anything. That is the boundary condition on the left that we have to prescribe. So we can note that the boundary condition would be that the u0 is equal to the ua. That is at the left boundary. Of course, we have propagation from left to right. Characteristics entering at the left, we have to get boundary condition. So, and now we can think a little bit, and then we will see what do we have here. We have here nj equations, and they are defining a linear system. Because we can now no longer determine the value at the new time level directly, as we could with the explicit method. We have now an implicit method, so that defines now a linear system. So then we can argue that this equation 37 that we can write the implicit upwind method in defines a linear system. And it defines the following linear system. The linear system of equations is, I call it 38. So now we have to get our matrix, get our unknowns, and the unknowns are u1 at n plus 1, u2 at n plus 1, and so on. And the last one is the unj n plus 1. So these are our unknowns. And on the right hand side, we'll have them, we'll see. If we start with j equal to 1, j equal to 1, then we see that we will get 1 plus c times u1. So it means we have to get a 1 plus c in the upper left corner. That will multiply by this. Then we have here minus c u0. u0 is boundary condition that we know. It is ua. We bring that on the right hand side. So we take the right hand side that we have. This is the u1 n, and then we take this also to the right hand side and use the boundary condition. We get here the current number times the ua, which is the left boundary condition. So then we have, and the rest is 0. So we have here only, this is all is 0. So then we have to interpret this as this times this plus 0 is equal to this. That is what it says, this equation says for j equal to 1. J equal to 2. J equal to 2, we get again this, but that is now getting in the diagonal here. That will now be here. 1 plus c will be here, because it has to multiply the u2. Minus c u1 at the new time level, that means we get a minus c here. And the rest again, 0. And this pattern will continue all the way through. So we'll have this all the way through until the very end. We have gain in the, for j equal to nj, we have again 1 plus c times u nj. So that will be the upper right, the lower right corner, the diagonal, minus c u nj minus 1. So it means we will also have a minus c here. So this will continue all the way through. And the rest is 0. All is 0. And what will be here? We have not done full job here. We go back to 2. We have simply u2 here on the right hand side. u2 at the old time level. Then we have taken everything into account for j equal 2. And that will continue until the last one. Then it will be u and j at the old time level. So that will be our right hand side. And thereby we have then defined the linear system that we have to solve in each time step. This we call the matrix A. This is our unknown vector u at the new time level, and this is our right hand side B, which essentially contains all at the old time level, but here the boundary condition enters. So this is the system that we get. And if we look at it, we see this is a lower triangular matrix, actually a bidiagonal matrix, because we have only something in the diagonal and in the subdiagonal below. The rest is 0. So that means we can solve this very easily. So, just take this. A is a lower bidiagonal. So bi for 2 matrix. And 38 can be solved what can this be solved? So the A has essentially the form of a lower, so it's, if you usually when you do the solution of this, you do a LU decomposition, usually with pivoting, but if you have the diagonal is dominating. We shall see that later on, diagonal dominant matrix. We have more in absolute value on the diagonal than the subdiagonal, which you don't need pivoting. And actually we have here just a lower triangular matrix. So this is usually done LU, but here we have already, it is already a lower triangular matrix. So, and then we just solve it starting from the first equation. This times this is this. So we can immediately get it by taking this and divide it by 1 plus c. So then we know the u1. Then we take the next 1 plus c times this. This is unknown. This we know already. Minus c times the known one is something known. So we take what we know already on the right-hand side, minus c times the u1 and the sum we know, and then we divide by the diagonal. So that is then we can continue there. So that means we use what is called forward substitution. So you remember that probably from in the algebra. So when you do LU decomposition, that is then the forward substitution. And then the algorithm is the following. This, as I just said, the value at u1 at the new time level is I call it b1, first component on the right hand side of b1 divided by 1 plus c. And then the next ones we can do, let's see, if you see it better if you write it here. So the uj n plus 1 is equal to, that is what we just said, that we take the value then at will be uj, let's see, it will be the ujn, that is what we have already on the right hand side, and then we add what we already know, that is the uj minus 1 n plus 1. That is the one that we have, imagine this is 2 then this is 1. And the 1 n plus 1 we have already computed. And then we divide by the value in the diagonal, that is 1 plus c. And this formula we can use all the way from 2 to nj. And then we have done our forward substitution and are finished. So that means what we see by this, that is then part of the solution of the linear system. In our case it's very easy, it's just this. In the usual case we would have to do this LU decomposition. We don't need to pivoting, that's all. Then we have to use this forward substitution, but then we have also to use the backward substitution. But here we don't need it because we have this simple bidiagonal matrix. In any case, this is additional work. Additional work compared to an explicit scheme. So, let's see. The break, let me tell you what we shall do next. So, then we know how to solve then the system, and we then know how to get the solution at the new time level. What we want to do after the break is we want to do a von Neumann stability analysis and then see what do we get for the modulus of the amplification factor telling us about the dissipation error, what will we get for the phase angle telling us something about the dispersion error. Okay, so then we take the 10 minutes break.